must confess that we have been chasing Manel for more than 1 year. So
yeah, I was busy with other stuff, but now it's a good moment, so I'm really glad that you come with me, and then I can share this introductory course on tribocorrosion to the audience, and I hope that it's interesting for most of them.
I'm sure it will do. It's tribocorrosion is kind of like black magic. There's not much. Oh, we'd say there are not that many people who work on that topic, but it's becoming extremely popular. So, and as you can see, we already have 57 people in the room, which is
very good.
Really high for our webinars. Yeah. Well, about the formats, no? Correct me if I'm wrong, Manel, but the idea is that there are 3 parts, and we have a little QA session after each of the parts, short one. And at the end, if there's some time left, we will just debate a bit and we'll just
exactly.
Cool.
Exactly. So I prepared the course in such a way that it's is useful for all people without any previous knowledge on corrosion. So that I will give a very short introduction to corrosion, the most fundamentals in a quickly way, so that you don't need to have any previous knowledge to follow the lecture. So it's very introductory, but I hope that everyone can follow it and that it's valuable for most of the professionals or graduate students, PhDs that are joining today.
Well, yeah, I have no doubt of it. Okay, as usual, just write. Okay, I know. Thank you. Just write down your question. If you have any questions at any point, just write them down in the chat, and we will read them afterwards, or we will unmute you, and you can just ask Manel directly. Very quick. Dr. Manel Rodriguez-Ripoll leads the research area wear reduction strategies at AC2T Research GmbH. That is the Austrian Excellence Center for Tribology. His main research focuses on surface engineering for reducing wear in extreme environments. Current topics of research of Manel, just by Googling a bit, I could find self-lubricating materials for high temperature. We also touch vacuum and also surface protection in tribocorrosive environments. So everything pretty nasty. I could find oil and gas, offshore, and lately a bit of biomedical. So yeah, pretty cool topics.
Correct, yeah.
Okay, well, about your life a bit, the bio. Graduated in physics at the Universitat Autònoma de Barcelona, so the Barcelona Autonomous University, and he holds a PhD at the Karlsruhe Institute of Technology in Germany. More than 80 peer-reviewed articles with an H factor of 32. Wow. Book chapters and 3 patents. Guest lecturer, several universities. Well, no, that's it. They can check his Google Scholar.
Can make it shorter, don't worry. We'll go for the stuff. Yeah. Thank you very much for the introduction. Thank you, all of you, for being here this afternoon. If you're in Europe, or this morning if you're in the States, or evening if you're in Asia. And I will share with you this this introductory course on tribocorrosion. So I hope the slides are now visible.
Very clear.
And just to start without any further ado, so the talk of today will be dealing with fundamentals of tribocorrosion. So it means it's an introductory course where I will explain the basics of tribocorrosion, which experimental techniques can you use to measure tribocorrosion in the lab, and how to interpret these results. And I have split the course in 3 different blocks, as Xavi already mentioned. So we have the first part of the course where I will give a very short introduction to the topic, and I will share some slides with you with some fundamentals of corrosion, because I think it's important that everyone can follow the presentation, even if you don't have any previous knowledge on corrosion, or you have very little knowledge on corrosion. The second part of the presentation will be dealing with tribocorrosion itself, so experimental setups, how do you measure tribocorrosion in the lab, which different methodologies you have, how to interpret these different data that you get, depending on which experimental setup that you have, with different models exist in tribocorrosion, And in the third part, I just showing some case studies of our research group. So basically, I will not go in too much detail. All of this is experimental work that we have published in the past years, and it's just like a snapshot on how can you exploit tribocorrosion techniques for several applications like material selection or material development or for coating selection. So starting with the first block, the introduction, I would like first to define what is tribocorrosion. So what we think is tribocorrosion. So tribocorrosion is the material degradation due to the action of wear in a chemically reactive environment. It means we have a material in a place that is chemically reactive, and wear occurs simultaneously with potential chemical reactions that can occur with the environment. So this can be because the material is in an aqueous solution, in an electrolyte, in an acidic media, because it's in hydrogen environment, because it's in ammonia, or because it's in CO2 or H2S corrosive environment. So this is probably the main difference with tribochemistry. So tribochemistry, you have chemistry because you have shear stresses. If you don't have the shear stresses, you don't have the chemistry typically. So it's a chemical processes activated by shear forces. In the case of tribocorrosion, the material reacts with the media, even if you don't have any mechanical wear. But when you have wear and the material simultaneously reacting with the environment, then is what we talk about tribocorrosion. And of course here we need to talk about a bit the kinetics of the process, because of course if you have a process where the wear is much faster, progressing much faster than corrosion, probably you can ignore corrosion, or vice versa. If you have a wear process that is much faster, a wear process that is much lower when compared to the corrosion progress, then you can ignore wear and probably you have a pure corrosion process. So this plays a bit, but basically what we will focus today is about the synergy, and this synergy is most visible in passive metals, because passive metals are metals that are corrosion resistant. So these metals are used to protect components against corrosion, and they rely on the spontaneous formation of a passive layer. And when we mechanically destroy this passive layer, then we have the paradox that a metal that should be corrosion resistant starts corroding. And that's the place where tribocorrosion is more obvious, and this is the place that tribocorrosion has most intensively been researched in the past years. And this occurs in many industries, ranging from biomedical to offshore, marine, the food industry, even in magnetic devices you can have tribocorrosion, in cutting tools, or you can have even desired tribocorrosion. So you can exploit tribocorrosion processes in chemical mechanical polishing for producing very smooth samples. So tribocorrosion does not always need to be negative. And the main challenge when we talk about tribocorrosion is that to select materials that are able to control tribocorrosion, to be tribocorrosion resistant, we cannot rely on separate corrosion and wear evaluations. So if we take a material that is corrosion resistant and we take a material that is wear resistant, we cannot automatically assume that this material will be resistant against tribocorrosion. And one paradigmatic example are titanium nitride coatings. This is a coating that has excellent wear resistance, is used in many cutting tool applications. It has also very good corrosion resistance in most aqueous environment, but is a material that is very prone to tribocorrosion. And you can see, for example, in this graph that the removed wear volume as a function of the electrode potential. For example, if you have cathodic potential, where mostly corrosion is inhibited, we have very low wear, which will be close to the pure mechanical wear. And when we apply an anodic potential, the corrosion, the tribocorrosion wear can be up to 2 orders of magnitude larger. So it means that we need to use tribocorrosion methods to evaluate materials that are suitable for tribocorrosion applications. So the separate consideration of wear and corrosion will be very often misleading. And in order to tackle this tribocorrosion challenges. I will give a very brief introduction to some fundamentals of corrosion very quickly. So a bit superficial, but that you know what are the main concepts that I will be talking later. And the most important thing to realize when we have metals exposed to the environment is that very often they degrade by corrosion. So we know, for example, the example of ships in marine applications, pipelines, bridges. So all these materials, they end up having this kind of rust because they react with the environment. However, many other materials, they are exposed to the environment, like this roof of the Guggenheim Museum in Bilbao, or these aluminum components, and actually they do not get any rust. So why is that? And this is because there are different processes here involved. So some metals, when they get exposed to an electrolyte, basically they dissolve. So you have a metal that turns into an ion and emits some electrons. Like for example, iron, you have here some iron piece, and some atoms of the iron will solve into the electrolyte and will emit electrons. However, other metals, they build up a spontaneous passive layer. So basically the process, if you make the sum, is the same. So a metal ends up having a dissolved metal, an ion, and some electrons. But this is done in two different steps. So the first step is an oxide formation. You have the metal reacting with water and forming an oxide layer with the emission of some protons and some electrons. And then in the next step, this metal oxide can dissolve, react with the protons, and end up dissolving and having water again. So this is, for example, the case of aluminum. That's the reason why aluminum components, they look shiny after the exposure to the environment. So aluminum reacts in aqueous solutions to form a spontaneous passive aluminum oxide layer. And of course, this oxide dissolution is very, very low, slow process. So that's the reason why these metals do not really corrode. And what happens with the electrons that we generate here in these anodic reactions? So, well, we need to have a cathodic reaction as well, where these electrons get consumed. So basically you have these electrons, and for example, if we are in neutral or alkaline media, we have the oxygen and water reduction equation, so that where these electrons get consumed, or if you are in acidic environments, the electrons can combine with protons available from the acids to form water. So basically, you emit electrons in the anodic reaction, and in the cathodic reaction, you consume these electrons. So basically, these reactions occur simultaneously. So without entering into too many details, we can already have a certain feeling that when we have an electrolyte with dissolved ions like natrium chloride or protons from an acid, or we have water, which is also a dipole molecule that can get oriented, and we already see that during metal dissolution we emit electrons. At some point we will reach an equilibrium with these electrical charges, and we will end up creating a potential. So this potential that we create in equilibrium is what we call the open circuit potential, the corrosion potential, that is spontaneously occurring when we immerse a metal into an electrolyte. And this corrosion potential depends, of course, on the electrolyte. It's not the same if we have a alkaline solution that we have a acidic solution. Depends on the metal itself, of course. Depends on the temperature. Depends on the microstructures. So the same material having different microstructures can have different open circuit potential. But basically, the open circuit potential is the spontaneous potential that is formed on a metal immersed in the electrolyte. So the reasons is what I mentioned before, this double layer and these metal electrolyte interactions. And what we can also learn from this open circuit potential is that in general, a noble metal, when we say a metal is not corroding, is because the open circuit potential is typically more anodic, so it's higher. This will be here, for example, the case of platinum with a very high corrosion potential, and the metals with that are less noble, for example, magnesium is a metal that reacts very quickly in aqueous media, so this has a very cathodic open circuit potential. And when you combine these two metals, you build a galvanic coupling, and then the metal with the less noble potential is the one that will corrode. So basically, it will act as an anode and will protect the other metal from corrosion. It means if you get, for example, copper or steel, and you contact it with zinc, zinc will be the anode and will corrode, and by this iron will be, or copper will be the cathode, and they will be protected against corrosion. But if you, for example, join iron or copper with platinum, then it will be the other way around. So platinum will be the material that is not corroding, and then the anode will be the iron or the copper. So that's important to know, that when you put a metal in an electrolyte, it dissolves, it emits electrons, and it builds open circuit potential. So if we have the metal and we have an open circuit potential, and if we want to change that potential, of course the metal will not like. So if we set the open circuit potential, the metal will like it, and we don't need to do anything. But if we want, for example, to increase the corrosion, so this potential of the metal immersed in the fluid, we will need to remove electrons, and by this we will increase the anodic corrosion. So basically we need to supply a current in order to support this potential, because they are not in equilibrium. And if we go in this way, so if we put an anodic potential, then what we are doing is that we are removing electrons from the metal, so we are promoting the anodic reaction, so we are increasing the corrosion of our metal. And if we apply a cathodic potential, so we put a negative potential, basically what we are doing is we're supplying our metal with electrons, so what we are promoting is the cathodic reaction, so at the surface of the metal, and then we have an increase in the current that is dominated by the cathodic reaction. It means that here in the anodic range, we are increasing the corrosion as we increase the potential, but in the cathodic domain, the current increase is not due to an increase of corrosion, but it's in an increase of the cathodic reaction, so that basically we are protecting the material against corrosion. And the polarization curves give us also the kinetics of an electrochemical reaction, so we can take what it's called the Tafel slopes. So basically we see that there is a regime here and here in this semi-logarithmic scale, where the current is related to the potential in the semi-logarithmic form. And if we take the extrapolations, for example, here and here, we can calculate the corrosion potential. We can see that close to the corrosion potential, these branches, they are not linear anymore. This is the reason, because here the anodic reaction is dominated, here the cathodic reaction is dominated, but here you have both of them simultaneously, so you cannot neglect the other one, and this curve becomes nonlinear. But if you take the extrapolation, you can get here the corrosion potential, and if you get, for example, the corrosion that occurs at the corrosion potential, you will get, for example, the corrosion rate of that material in that electrolyte under open circuit conditions. So this is what would happen for an active material. For a passive material is slightly different. So for a passive material, the cathodic domain is the same. So we have the cathodic reaction, and it looks very similar. But if we just plot the anodic domain, we may have something like this. So the passivity is the formation of this spontaneous oxide layer that is protecting the material against corrosion. And in this cases, this anodic branch of the polarization curve, when we apply a potential, may occur that at the beginning, not always, but it may occur that at the beginning we have an increase in the current density. So it means that we are corroding more the material when we apply a voltage, but one of a sudden we have what is called the active-passive transition, and at some point the current becomes very, very low. So we have a region with a very low current density. It means that the corrosion is very, very, very slow. And also the current density is independent of the applied potential. So we can increase the potential, but the current density remains the same. And the reason is that when we apply this potential by the reaction that we saw before, we are increasing the thickness of the oxide layer with increasing potential, and this occurs until we have an unstable passive layer that starts to break down, and this is so-called the breakdown potential. And here we have a very fast increase in the current density, and this current increase may not be only due to the breakdown of the passive layer, but may also be related, if the potential is very high, due to water splitting. So we may apply such a high potential that we are splitting the water in the electrolyte and forming hydrogen and oxygen. So just for completing this, active passive transition is not always occurring in all metals, so it is often observed in acid solutions, but it's not obligatory to have it. Depends on the metal and the electrolyte. So in other metals or natural solutions or basic solutions, you may go directly from the corrosion potential. So you have here the cathodic branch, then the corrosion potential, and then you may go directly into this passive domain, and then with increasing potential, you end up going into the transpassive domain. So when we put a metal in an electrolyte, we dissolve the metal, we produce electrons, we have an anodic and a cathodic reaction. We may have the formation of spontaneous passive layer. These reactions and these phenomena result in the spontaneous formation of a potential. We can modify this potential, but we need to put an increase, so we need a driving force to change this potential. And when we change this potential by adding a current, we can make these polarization curves that give us information about the kinetics of the reactions. But if we take into account only the thermodynamics, we can also have something that is called the Purvo diagram. And this Purvo diagram are nothing but a potential versus pH diagram. In this case, the example is shown here for iron. And these are obtained under equilibrium. So, and these diagrams, they tell us, for example, for an applied potential or for a certain open circuit potential, as a function of the pH, which chemical reactions will be favorable, or which chemical form will be favorable. For example, if we have iron, in this domain we will have passivity. So for example, here at moderate pH we will have the formation of Fa2O3. Here at lower potentials and higher pH we will have Fa3O4. Here we will have a very high pH corrosion. Here under cathodic protection we have immunity. And we can have this, for example, this representative way. This was written by a colleague of Marcel Purvo that invented these diagrams, and in a graphical way that you have regions for certain applied potential and pH where you have passivity. So you put the corrosion devil into the jail, thanks to this passive layer formation. And here we have cathodic protection. So here basically we are breaking the tools of the devil, of corrosion devil, and here we have immunity due to cathodic protection. Here in this little regime here where we have corrosion at very high pH, then we also have the devil again. So that's a funny way of how to read a Purvo diagram. But the Purvo diagram gives us information about which reactions are thermodynamically possible, but does not give us any information about the kinetics. So the kinetics is given by the polarization curves. So this is a bit the information that I wanted to give about corrosion. So we will use now these concepts in the next part of the presentation. If there are some questions, maybe a short question, 2 or 3, I can reply them now before proceeding. If not, at the end, I will also be available for further questions.
As far as I know, I don't see any question in the chat.
Yeah,
No?
no questions. Maybe I can ask one interesting for me was about this titanium metal. So in this graph from corrosive metals, it was one of the good ones, but then you also mentioned that it sometimes still corrodes. So I'm wondering, why is that?
No, this So basically, when you have these passive metals, you still have dissolution, but of course this dissolution, the rate of this dissolution is smaller. So you still have metal dissolution, but this dissolution is done in two steps. So first you have the oxidation formation, so the oxide formation reaction, and then you have the oxide dissolution formation. So you have an equilibrium where part of this aluminum or titanium ions are solved in the electrolyte, but of course the corrosion rate is much smaller than if you put, for example, magnesium in an electrolyte, where the corrosion rate will be much larger. But even for passive metals, you still have some ions going into the electrolyte and reaching an equilibrium between the ions dissolved and the ions reabsorbed in the electrolyte. So it's basically the same, it's just the rate that is different. So the process is the same, but the rate is the big change here. The corrosion rate is the key.
That layer, is that weaker? So
this layer in passive metals typically has a few nanometers. We're talking maybe 2 to 5 nanometers. And depends on the conditions how this passive layer is formed and the electrolyte. Where the material is immersed, but typically it's a ceramic. So, for example, in aluminum is aluminum oxide, titanium is titanium oxide, but it can be break, of course, during rubbing, and it does break. And that's the reason why when you break this passive layer, you expose the naked metal to the electrolyte. And then, of course, the corrosion rate will not be this one, but will be something closer to this. So that's the point here.
Thank you.
Yeah. So there are two questions. The first question is, how does it work for reactive gases like hydrogen, the corrosion? And the second question is, how long should we keep the material in the electrolyte so that it reaches the OCP?
Well, the corrosion potential, it can take quite a long time. So typically in tribocorrosion experiments, the most typical times that I use for stabilizing the OCP is 30 to 60 minutes. But basically here important is that the rate of variations, because you have a trend, so actually it's a tendency to reach equilibrium, but you will need infinite time to reach it. But when the OCP is changing less, for example, than let's say 1 millivolt per minute or something like this, you can then stop and consider the OCP to be stable. But typically 30 to 60 minutes could be sufficient. It depends on what you would like to do and how do you need to be stable. For example, if you do some cathodic cleaning, so you cathodically remove the passive layer and then you rebuild it again within the electrolyte, you may get more consistent results and might be quicker. Or if you pre-treat the sample with some acid, for example, with nitric acid before the experiment, you can go quicker. So it depends a bit on the system that you have. And the other question regarding hydrogen, this is a bit different. So this would be current research, but basically hydrogen is reacting with materials, with metals by embrittlement. So typically you produce hydrogen embrittlement at the grain boundaries, segregations, and here the tribocorrosion would arise since this embrittle surface layer has different properties than the bulk material, and the wear rate will be different if you compare the embrittle layer with the non-embrittle one. But this is slightly different than what I will be presenting today. So today we will be talking about metallic materials passive immersed in an electrolyte. But this will be the same. So basically a reactive environment and the wear occurring in the reaction layer, in the reaction scale, or in the corroded zone, having different mechanical properties, different microstructures than the rest of the bulk material.
Cool. With that, we reach half the talk, so it's 3:30. So there are 2/3 of your talk to go, Manel. So I suggest that we move on.
So we will continue. So now I would like to talk about tribocorrosion itself. So about some experimental techniques and how to interpret the results that you get in tribocorrosion and which models exist. So the most simple tribocorrosion experiment that we can think about is, I guess, is that you have an electrolyte, some seawater, some acid, or some reactive environment. We have a metal immersed in this environment. We have a ball or a counterbody. We load and we start sliding. So by this we will impart the tribocorrosion, and at the end of the experiment we can see how much is the tribocorrosion wear. We can see the damage mechanism. We can see, for example, with SCM how the wear scar looks like. We can check with XPS how the chemistry of the wear scar looks like compared to the unworn part of the wear scar. We can see how the microstructural evolution is occurring in the cross section. So we can really learn a lot of things, but still we cannot learn enough. So we have seen that when we put this metal in the electrolyte, we are having the spontaneous formation of one potential. So maybe one thing that would make sense is to see what happens with this potential. So measure this potential, track it, and see how it's evolving. And for this, we need a setup that typically looks like this. So we have a tribometer coupled to an electrochemical cell. And in the electrochemical cell, we have 3 electrodes, can be 2 if you don't need to measure currents or to apply any voltage. This 3 electrode electrochemical cell has a reference electrode, which is an electrode with a known and a stable potential, where all the potentials will be referred to. We have a counter electrode, which is a noble metal, typically platinum, can be graphite, for example, and the working electrode will be our sample. And this 3 electrode setup is connected to a potentiostat that can measure the voltage or can apply a certain voltage by triggering some current. And then you have a data acquisition system to acquire the data of the potentiostat and the tribometer, and by this you will measure what happens with the current, the potential, and you can also monitor coefficient of friction and other typical parameters that you have during a tribological experiment. And what we very often use, this white little fellow here is a aluminum oxide ball. So typically in tribocorrosion experiments, we use aluminum oxide or a ceramic counterbody. The reason for that is because we wanted to have a stable counterbody that is not wearing too much. And another reason is also that we don't want this counterbody to be creating a galvanic coupling with our sample, because we have seen that when you have a galvanic coupling, you may change the cathode with the anode depending on which material you use, so you can change basically the electrochemistry of the system. So that's why it is very often preferred to have a aluminum oxide ball. So it's not a must, but it's much easier to interpret the results if you have a inert counterbody that is also not participating so much in the damage, because it will typically not wear. And if we do something like this, for example, in that case, if we have only 2 electrodes, we don't need to apply any voltage. So we do the same experiment as before. So we have a ball, a plate, and everything is sliding. And now the only difference is that we measure the voltage between the reference electrode and our sample. Then we can see this, we can track this spontaneous potential that is built by this metal, which is the open circuit potential. And we can see that this open circuit potential here before the experiment, before the sliding, it's stable, has a certain value. And if we have a very little load of 10 millinewtons, when we start the sliding, basically nothing happens. It means that we don't have any change in the passive or in the surface composition of our material. If we apply a higher load of 100 millinewtons, then we see that we have a shift of the open circuit potentials towards cathodic values. We see that this is not stable, so we have the potential sometimes convex to higher values. So the depassivated area tries to repassivate again, so you have these instabilities here, and at the end of the experiment, the open circuit potential returns to the initial value because the material is repassivating. So basically, you are in the same electrolyte, so the material builds up spontaneously again this passive layer that was mechanically broken to establish the same equilibrium condition that was at the beginning, having the same potential as before sliding. And if we apply a higher load, then we fully depassivate the material, then the material remains almost fully depassivated more or less constant throughout the experiment, and at the end of the experiment, the open circuit potential returns to the equilibrium potential that occurred before sliding. So this could be something that you can learn, for example, by monitoring the open circuit potential. So this drop in potential is caused by a galvanic coupling. We have seen before, we have talked before about the galvanic coupling. So basically when we depassivate the passive metal, so when we mechanically break the passive layer, then we expose the naked metal to the electrolyte. It means that the wear region becomes anodic, so then we have the anode there, so the metal is corroding there, and then the cathodic reaction, so we saw where the electrons get absorbed, are occurring in the cathodic region, which is outside the wear scar, and then this galvanic coupling between the wear scar and outside the wear scar is the one responsible for having this drop of the open circuit potential. And you see that this shift is toward cathodic values, toward less noble values, because our material gets less noble. And we'll maybe not enter into many detail. You can also get quantitative data from open circuit potential experiments. It was proposed in this model that was published in Corrosion Science 12 years ago by Vieira and collaborators. And the model is what I basically relies on what I mentioned now. So you have the depassivated area that can be fully depassivated or can be only partly depassivated here, and then you end up building a galvanic coupling between the non-passive part and the passive ones. So this one behaves as an anode, this one behaves as a cathode, and under OCP conditions, we don't have any current. We have seen before that it's in equilibrium. We don't have any current. We need to have a current if we want to impose a potential. We have seen this in the polarization curves, but locally we have currents. This current is zero, but we have locally currents that they cancel each other. It means that the current density, the anodic current density, is equal to the cathodic current density, and this current density is the total current normalized by the area. And if you assume this electroneutrality and this Tafel kinetics that we have talked before, these slopes of this anodic and cathodic branch, you can end up having some equation like this, where you know that your anodic area, which is basically the worn area, the cathodic area, which is the area outside the wear track, you have these Tafel coefficients that you can get with these slopes experimentally, and basically by knowing all of this, then you can correlate, for example, the cathodic potential. If you know the corrosion potential, see how the cathodic potential evolves with time. And the only parameter that here you wouldn't know is the anodic current, that it's the anodic required, or that it's triggered every cycle for repassivating the worn area. So you can track or calculate or estimate this current density, this anodic current density, by plotting, for example, this data. So this is a quantitative model. You have all the questions here in the paper with all the explanation, but you can get also quantitative data out of these open circuit potential experiments. It's usually not done, so typically OCP experiments are discussed qualitatively, but it's possible to get quantitative data. The place where typically quantitative data is usually obtained is using potentiostatic experiments. So with potentiostatic experiments, we are forced to have 3 electrodes. So we need to have the material that is investigated, which is the working electrode. We have a counter electrode that is typically a noble metal, a platinum or graphite, and the reference electrode, stable material not reacting with the media with a well-known potential, where we refer all other potentials. And if we wrap here and we apply a potential, we saw before that in the passive domain, when we apply a potential, the current is very low, in contrast to active materials, where we saw this branch, this anodic branch, where the current was logarithmic, so exponentially increasing in this semi-logarithmic plot with increasing voltage. So here in this polarization course, we have seen that the passive materials in this semi-logarithmic scale, the passive domain, basically the current density is independent on the applied voltage and is very low. It means that if we apply this passive domain voltage, for example here, plus 0.5 volts, to titanium in synthetic seawater, the current is very low because we have this dissolution, but it's very small compared to active metals. But as soon as we start rubbing, we then trigger corrosion, and then we can have a higher current that we can measure with the potentiostat in the same way that we did in the polarization course. The only difference is that the potential here is constantly applied. That's what is called a potentiostatic experiment, so with a constant applied potential. And we can have similar observations. So we have 10 millinewtons, basically nothing happens. If we have 100 millinewtons, we can see little current occurring in the wear track due to the currents generated by depassivating the wear track and exposing the naked titanium to the environment, and then having this active dissolution of titanium. And if we have higher load, then the current will be larger. And here it's what is typically done to get quantitative data is to integrate this current, because when you make the integral of the current, you get the charge. And by knowing the charge, we will see that you can get the corrosion. And one of the most common models used to interpret this data obtained under potentiostatic conditions is the model proposed by Ulich in 1954. And basically, it assumes that when you rub a passive metal, you destroy the passive layer, and the total remove wear volume by tribocorrosion has basically two contributions. One, that it's done to mechanical wear, so the formation of wear debris, as we would have in other wear experiments, and the chemical wear here. And the chemical wear outside the wear scar, we can neglect it, but we have seen that passive metals, the metal dissolution, passive dissolution is very small. And we can assume that most of the chemical wear is coming from the depassivated area here in the wear track. And these potentiostatic experiments that I show under passive applied potentials, basically we can measure the total remove volume at the end of the experiment. So this is the volume that we would measure using profilometry or confocal microscopy. The chemical wear, we can calculate it using the Faraday equation. So we have the charge, which is the integral of the current that we measure with the potentiostat. We have the atomic mass of the metal, we have the balance of the metal, we have the density. So these are the constants that we can check in books that are well known for the metal that we have. And the Faraday constant is also well known, so we can calculate the chemical wear. And when we know the chemical wear, because it's calculated based on the potentiostatic data, and then the total volume is calculated using profilometry, then the difference between both of them gives us the pure mechanical wear occurring due to the formation of wear debris. And then you can make, for example, this kind of graphs where you plot the total wear volume as a function of the potential, and then you can see, for example, that with increasing potential, the total wear increases because we increase the thickness of the passive layer and we destroy this passive layer. So basically we're promoting the formation of a thicker layer when we apply a passive potential and then automatically destroy. So we have here disrupted synergy. So we have the highest wear here in the passive domain. In the cathodic domain, we have the lowest wear. And since we are under cathodic protection, so we are inhibiting the anodic reaction. So we have here mostly wear that it's imparted by mechanical wear, and as we move it towards the passive domain, the contribution of chemical wear gets more important. And this is something, for example, that you can check for a certain material in a certain electrolyte, and then you can understand how the material is degrading under tribocorrosion conditions as a function of the applied potential in the different electrochemical domains. There is another model that it's originating from the erosion corrosion community that it's called the synergistic model. So this model, the approach is similar, but it's somehow slightly different. So basically this model assumes that the total loss due to tribocorrosion, erosion corrosion, or whatever, so the total mechanical wear in a corrosive environment has three contributions. So a pure mechanical wear or erosion, a pure corrosion term that it's only due to electrochemical process, and a synergy term. And this synergy is the action of the combined mechanical and corrosion processes, and this synergy you can disclose it in two additional terms. One that could be the corrosion enhanced erosion or wear. So the wear due, it is enhanced wear due to corrosion processes. For example, because your material gets weaker, because it gets corroded, and this erosion enhanced corrosion that will be something related to this wear accelerated corrosion. So the corrosion that it's triggered by this mechanical damage of the passive layer. Then you can measure, for example, here the total wear is the one that you measure on the profilometry. The corrosion rate under the absence of wear, you can get polarization curves without rubbing. This E with the pure mechanical wear is the wear that you could get under cathodic protection, and this synergetic term of wear, so this erosion enhanced corrosion is, for example, you can get it under polarization curves during the wear process. So the main critics with this model is still very widely used in literature nowadays, but the main critics arises that with the difficulty to interpret these terms, so to have a real physical meaning for these terms, and also the challenges to get these quantities experimentally. Because if you want to get, for example, pure mechanical corrosion, pure mechanical wear, then you apply cathodic protection, but it's known that depending on the cathodic potential that you apply, you may change the wear rate. So then which is the correct wear rate? So because depending on the cathodic potential, if you start, for example, generated hydrogen in the cathodic reaction and your material is sensitive to hydrogen embrittlement, you will change the wear here. And therefore, it's not very well defined what does it mean, this pure mechanical wear, just by applying a cathodic protection. So you can change depending on which potential you apply. And also, to get the polarization curve during the wear experiment, you have the problem that the polarization curve takes some time to be measured. So normally the scan rate is small. And during this time, you can trigger the formation of wear debris, you form third bodies, you change your microstructure. So maybe at the end of your polarization curve, your metal is different than it used to be at the beginning. So this is, these are probably the main critics of this model. So the difficulty to get these terms independent from each other and their accurate physical meaning. But it's still widely used in literature, and then you can make, for example, this kind of maps as well. So, for example, you have the particle velocity in erosion processes as a function of the applied potential, and you can see, for example, that for cathodic potentials, you can have here pure erosion because you are under cathodic protection. You can have places where erosion dominates at very high impeachment velocities. Other places where you here, for example, if the particle velocity is very small, then you are dominated by corrosion, and you have also here intermediate states. Or you can also make different graphics where you, or different maps where you can plot the particle velocity as a function of the particle radius, for example, if you have different types of abrasives, and you can get all these kind of different maps. So you can get a lot of valuable information. But as I mentioned, the model of Ulrich, at least for me, that when I show this mechanistic model, seems to be easier and more straightforward to interpret and to get data quantitative. And the last slide here is just to show what is determining tribocorrosion wear. And probably you can figure out if you have following the last slides. So there is this very nice paper from Stefano Misler and Ana Muñoz, where they make a big assessment of different experiments performed, tribocorrosion experiments performed on the cobalt chromium for hip joints using model experiments, tribometers and simulators. And you can see that as a function of the contact pressure, there is a certain trend to increase the wear, but it's not really always the same. And you can see that the wear typically in a tribometer, the wear rate is much higher because usually you have point contact, and here on the simulators you have more conformal contact. So basically, this data looks really difficult to interpret if you plot the wear coefficient as a function of the contact pressure. But if you plot the same data as a function of the electrode potential, then all this data collapse in a master curve. And this is what I was mentioning before. So under cathodic applied potentials, the wear is the lowest in tribocorrosion, and as you increase the voltage and you go into the passive domain, so when you have an applied passive potential is where you have this most destructive synergy between wear and corrosion, because you are triggering the formation of a passive layer with increasing potential, even a thicker layer. And of course, if you mechanically destroy this passive layer and continuous building and making this continuous process, at the end you will end up having the most dangerous synergy and the highest wear in this process. But this kind of master curves in tribocorrosion, they are well known. So you have lower wear in the cathodic domain, the total wear we are talking here about, and the highest wear in the passive domain. So with this, I am at the end of this second part, and I will be willing to reply some of your questions now.
Yeah, there are some questions, but they are for the previous section. But yeah, I think maybe we can go through those. So what are the prevention measures for tribocorrosion in ferrous metals?
What are the... so basically what you need to do is to select a metal that it's degrading the less possible in the medium, so that it has a good passivation kinetics. And for example, that it's inert. I was doing a couple of years ago a review on coatings for tribocorrosion applications, so thin coatings. And for example, we saw today that titanium nitride has a very poor tribocorrosion properties. On the other hand, for example, DLC, which is a more inert material, performs much better under tribocorrosion applications. So one possibility, for example, is to have a material that has different kinetics. For example, chromium nitride is a material that also, due to the repassivation kinetics of the material, is very suitable for tribocorrosion applications, and chromium nitride coatings perform much better when compared to titanium nitride under tribocorrosion applications. So you can use different materials, but the tricky point here is that you cannot rely on pure corrosion or pure wear experiments to determine which of these materials is going to be the most effective for tribocorrosion protection.
Thank you for the answer. And another question is, how do tribocorrosion open circuit potential occurs for magnesium alloys?
So magnesium alloys are very active. So they readily corrode in most of the aqueous media. So that's the reason why they are used for biomedical, so solvable medical implants. And here, of course, the solubility is also conditioned by the potential. In the case of active metals like magnesium, the things that we have shown today is slightly different. So there are some nice papers written by the colleagues from Techniker, publishing a few years ago, where they compare active with passive metals. In the case of passive metals, it's different, so you don't have a shift towards cathodic values of the OCP during rubbing. You have the opposite, so you have a shift towards anodic values. So basically, you switch the cathode and the anode in the sample. So you have a change in that case of active metals. The anode is the outside of the wear scar and the cathode is inside of the wear scar. So in some of these metals, like these colleagues show for carbon steels, during tribocorrosion, you're actually promoting wear outside or you're accelerating corrosion outside the wear scar. But that's with active metals is a bit different story to what I showed today. So you can still use the same tools, but the concepts are a bit different because you don't have this concept of depassivation and this. There is still this galvanic coupling, but it's different.
I see there is a hand raised by Donna. I'm not sure, Donna, if you want to ask a question.
Yes, thank you very much for The presentation is very nice. I do some work related to tribocorrosion, and I'm using potentiostatic methods. So basically, we want to calculate the wear due to corrosion and the wear due to mechanical wear, basically, and separate them. So I'm doing similar to Michelin tribocorrosion on cobalt chromium for hip implants. And what I've seen is that when I'm leaving it for 30 minutes to settle basically the potential before I'm rubbing the material, sometimes it doesn't set at the same corrosion range. And then what happens is, because my contacts are so small, the difference that it makes where it settles is huge in between samples. So how can we avoid that our total volume wear due to corrosion has massive differences just because it settles in different kind of potentials?
So you mean that the samples are different in size, you mean, or that they are very small?
All of the samples. All of the samples are the same, and the conditions are the same as well. But when we are passivating it, then basically it doesn't passivate for 30 minutes at the same range of potential. And then when we start rubbing it and take the curve underneath to calculate the volume loss due to corrosion, then what happens is the differences are very high compared from one sample to the other.
So you're meaning you're talking about the OCP or about the potentiostatic? Because you said potentiostatic. So it means you apply anodic potential typically.
Yes. Yes.
And this current that you measure is different. Because the potential is the same. The potential is the one you applied.
Yes.
Okay. So theoretically, if you do everything correct, I mean, the open circuit potential of cobalt chromium can slightly vary between different samples, depending on the conditions how the material was passivated. This can improve the consistency of this open circuit potential measured at the beginning if, for example, you passivate before with nitric acid, or if you do cathodic cleaning before the experiment. But the current during rubbing should be basically the same if you are doing everything correctly. So, because this current during rubbing is the one that occurs due to the passivation. So here it only matters the size of the wear scar, and if you have the same conditions, even if you have different samples, should be the same.
I think in my case, what happens is because the contact, my point contact is very small, since we are doing micrometric ball on the sample. So basically, the current change is very, very small. So if it's settling, like if you would check it in a microscopic, or in a bigger scale, then it wouldn't make a difference. But if you're looking at another scale, then it's actually a big difference.
I mean, to measure the current, the sample should be properly contacted. Of course, if you have a contact that is, or the contra electrode is too small, for example, so the contra electrode should be at least 5 or even better 10 times the area of your working electrode, and the contact should be enough so that you are able to capture all the current that is formed during rubbing. Of course, if you have problems with some bottleneck in the system, then of course you will not be able to measure all the current that you are measuring, and then the results will be inconsistent. But it sounds to me like it's a problem of the setup.
All right. Thank you very much. I'll have a look.
I need to say something. I'm so sorry. There are so many questions. I think that and there's one part to go. We have been running for 1 hour.
Let's just do one more question. Let's just do one more question from Hossein, because I see his video. Let's see what he wanted to ask.
Thank you very much. I have some question about the test and experiment condition. About the, for example, ball diameter, about the levels of the force of applying to the ball on the contact surface, and about the ball material. This condition is constant, or maybe it's different for different situation or materials?
No, this depends fully on what you are willing to investigate. I mean, which contact conditions are you willing to reproduce with your applied contact load? The electrolyte selection depends on your application or your purpose of the study, and the selection of the contour body the same, and you will select different load and different diameter of the ball based on the contact pressure you would like to achieve. And yes, it depends basically on your application and the aim of your study. Nothing else. You can use any arbitrary contact pressure or any arbitrary electrolyte. Just what you want to study.
Thank you. Thank you very much.
Yeah, thank you for asking.
Thank you.
Now we need to take a decision, and I think the only one who can take the decision here is Manel, because you are our guest and you told us that you had 1 hour. There's a third part, we know, we'd love to see that. Do you want to have a second round with us?
For me I have time. I don't know if you want to continue now or...
Fine for me. We are very thankful for that. So,
otherwise
we put it next week or whenever you have time.
No, for me too. I mean, if everyone is here and they don't have any further appointments, most of them I can go quickly through these case studies, show them. Everything is published. I give the references here, so you come back to me if you have any further question.
Lovely. Thank you for that, Manel.
So we can move to the first case study, which is the fire water valves for offshore platforms. So you remember this accident of the water horizon, this water spill that make a big problem in the Gulf of Mexico. And in order to avoid this kind of catastrophic failures, the new platforms, they are forced to have some fire water valves able to pump seawater in case of fire. And these fire water valves, they are made of titanium, and they need to be tested. I think it was once per month to be sure that they are working, and they need to be operational for 10 years. So since titanium has very poor wear performance, so the corrosion properties of titanium are very good, but the tribocorrosion, they are not so good. We were here dealing with how to select a suitable surface treatment for these fire water valves. And here is an example on how you can use these very simple open circuit potential experiments for screening different surface treatments. So we were evaluating DLC coating, so tungsten dope DLC, thermal spray coating deposited by high velocity oxygen fuel, and a nitrate layer done by ion implantation, so by plasma nitriding. And basically what you can do with these different materials, using also titanium as a reference, is you make open circuit potential experiments, as we have seen before, very simple. And from these open circuit potentials experiments, what you can get is the evolution of friction as a function of time for the different surface treatments, and the evolution of the open circuit potential as a function of time. So you see here the different OCPs before rubbing, and the OCPs during sliding and after sliding. And based on the OCP behavior, based on the friction behavior, and based on the total wear that you measure at the end of the experiment, you can use this data for making suitable selections. For example, we see that the nitriding layer has a very high and very noble open circuit potential at the beginning of the experiment, but this potential dramatically decreases. The reason is because you will break this nitride layer during the experiment, and then of course the material will become even less and less noble because you go into this diffusion layer where you have titanium combined with some titanium nitrides. And at the end of the experiment, we will not be able to repassivate because basically this layer is gone, is destroyed. So that's why the open circuit potential at the end of the experiment is lower when compared to the initial one. With titanium 6,4, you see that the OCP at the beginning and at the end of the experiment is the same. And what you can observe, for example, is the thermal spray coating and the DLC at these investigated low contact pressures that were very relatively small. So we were using a bowl, I think, with 50 millinewton bowl, 50 millinewton contact pressure. So we can see here that there is basically no change in open circuit potential, indicated that there is no change in the surface condition of these two surface treatments during the experiment. And based on this information, based on the total removed wear volume, you can get this data for making a decision on which material can have the best tribocorrosion performance. Another case study that I would like to share with you is the design of materials that are resistant for tribocorrosion applications deposited by laser metal, so for additive manufacturing. The reason behind was that we were working with a 316L stainless steel, which is a material similar to titanium 6.4 with outstanding corrosion resistance, good biocompatibility. It's very affordable compared to titanium, and it can be also deposited by additive manufacturing, but it has very poor wear and tribocorrosion resistance. And the idea was, is it possible to improve the tribocorrosion resistance of this 316L? And this was done in collaboration with Fraunhofer Institute of Ceramic Technologies in Dresden. They developed this titanium carbonitride nickel powder. So we selected titanium carbonitride because titanium carbides or titanium-based carbides are sustainable. They do not rely on critical materials, and they have very low density and an affordable price. And what we did was investigating different composites or different cermets having a 316L matrix with different concentrations of this titanium carbonitride. One thing we checked, for example, was that the material doesn't lose passivity under static conditions without rubbing. So we are not rubbing anything here yet. So this is just the polarization curve. And we see that this material, 316L, has a passive domain, and these other ones containing 30 and 40% of titanium carbonitride inclusions, they still have a passive domain. The only price to pay is that the transpassive potential, so the breakdown potential, shifts towards cathodic values. It means that this material will be a bit more prone to pitting, because of course you have some defects, and these defects will be initiation sites for localized corrosion, but still you have passivity, so this is quite good. And I'm showing here, for example, the wear scars after the tribocorrosion experiments. These are OCP, so we didn't do anything, just following the potential as it was established automatically, spontaneously. And you see that with increasing concentration of titanium carbonitride, the tribocorrosive wear volume gets smaller for higher concentrations of titanium carbonitride. This is even true if you apply a passive potential, even though if you compare passive potential with OCP, you see what we saw before, that under an applied passive potential, the wear in general is larger, but even under these more detrimental conditions, the material performs much better when compared to the unreinforced 316L. So you can also use the same concepts of this OCP experiment, these potentiostatic experiments, for investigating or designing tribocorrosion resistant materials. Another thing you can do, for example, is to get this kind of measurements that we did at 3 bar CO2 pressure. So this is a bit different. So we have natrium chloride at 3 bar of CO2. So we have CO2 corrosion. Is slightly different. I will not enter into much detail. So we are having the formation of iron carbonates because we don't have oxides. So we are promoting, for example, here for the iron alloys, the formation of carbonates, and we don't have oxygen here dissolved, so that we are working under anoxic conditions. We were evaluating different corrosion-resistant coatings, also wear-resistant. And it's interesting to see here that for these different coatings, in principle, there is a certain trend that the tribocorrosion wear volume gets smaller for increasing hardness. You can see there is a certain trend, but you can pick up 2 materials, for example, this iron-based alloy material here, or this nickel-based alloy material, and these coatings, they have very similar hardness, around 800 Becquers, but this one has much lower tribocorrosion wear under CO2 conditions when compared to this one. And the reason for this is something I didn't touch today too much, but it's very important also in tribocorrosion, is to check the microstructure after the experiments. And you can see here, this is a cross-section. This is the sliding surface. You can see some sliding grooves. And what you can see here is this iron chrome boron silicon plasma spray coating is prone to selective corrosion along the grain boundaries. That is the responsible for having this poor tribocorrosion wear performance, whereas this nickel chrome bore silicon, you can see that in the wear scar you hardly see any scratch or any groove, and in the cross section you can see maybe some superficial cracks, very small ones, but very little damage. And that's the reason why these two materials, despite having exactly or very similar initial hardness, one of them is much more prone to tribocorrosive wear when compared to the other one. And to conclude the last case study, I would like to show something that it's one of my favorite projects is about tribocorrosion of partial implants. So a partial implant is basically a localized replacement of damaged cartilage. So instead of having a full knee replacement, you have only a little part here of cobalt chromium that it's placed to replace damaged cartilage locally, but the rest of the joint is left unaffected. And the problem here is that you create a metal on cartilage interface, and we were asking ourselves if you have also metal release or tribocorrosion here in a cartilage to metal contact, cartilage being very soft. And what we did here was in vitro experiments, quite challenging. So we were having not only the mechanical wear under control, also the electrochemical conditions were kept under control, but also the biological. So we were having live samples from a bovine that were immersed in this solution, that it contains nutrients, contains antibiotica to ensure that the cartilage is alive. So we can keep the cartilage alive for a couple of days. We tested all the samples within the first 2 days after extraction and use these cobalt chromium cylinders as a counterbodies. Here you can see this is the reciprocating sliding setup. This is the counter electrode, the reference electrode. And you can measure, for example, the friction, which is 0.03, so very smooth, very low friction. So cartilage is an excellent material. Then the guys from the medical faculty, they can do this cartilage gene analysis. So basically you can see if the cartilage feels good for certain sliding conditions, or doesn't feel good. So this is, for example, some genes that are expressed depending on the conditions. In this case, for example, they are cartilage-specific genes, and these cartilage-specific genes, it means that the cartilage is happy, so they get stimulated if we are applying physiological conditions. And another thing that we can do, for example, is track the OCP during sliding. In this case, we have this group of samples that were just treated as received. So the OCP, you can see that there is a certain oscillation of the OCP for initial samples. These ones here were treated with nitric acid. That's the reason why the passive layer was different and was higher. But independently of the initial condition, we can see that there is a little drop of OCP at the onset of sliding. These are the different animals that we tested. And this drop of OCP means that we are having metal release, so cobalt, and we could also check, for example, using high-resolution mass spectrometry, that this cobalt was found to be bound to amino acids. So you can also use these tribocorrosion methodologies with in vitro setups for tracking biomedical implants or evaluating the performance of biomedical implants in vitro. So these tribocorrosion setups, they are very powerful. It's very important to use them when you want to evaluate materials for tribocorrosive environments. So never rely on separate corrosion and wear assessment. So it should be always done in combination. It doesn't matter if you measure OCP or current or anything, even if you don't measure anything, as we saw in the most simple experiment, but you should have tribocorrosion conditions. And at the end of my talk, I just would like to share some books in case of you would like to get further information. So there is this book on tribocorrosion of passing metals and coatings. It's from 2011, I think, 2012, so 12 years old, but still an excellent reference book for getting all the models that I explained today. There is some chapters also on fundamentals of electrochemistry, fundamentals on passivation, so a really good book. This one is a similar book but focused on biomaterials. And then there are these two newer books. This book here is an introductory textbook, very short, very didactic, so suitable for maybe undergraduate students or graduate students that would like to learn about the topic. And this book here is a recent book where I wrote a a chapter on tribocorrosion of thin coatings. You can get most of the books here. For example, these three. You can get the Manel chapters. So most institutions will have access to all these chapters of these books. This one is in Springer, but you can also get legal access to most of the chapters through your institution. And there are also some conferences where you can learn more and get into touch with other people working on tribocorrosion. So there is the annual meeting of the European Federation of Corrosion, this working group 18 tribocorrosion, where I am involved, and we are having every year at this annual meeting of this Eurocor, we have a tribocorrosion session. Next year will be in Norway, so we'll be willing to receive your research, your contribution. Keep in touch here with all the researchers. So we have a lot of colleagues joining every year here at the Eurocor. And we are organizing also a special conference next year in Vienna in 2025 in October, which will be a conference on tribocorrosion, where we would like maybe to address these new topics that I didn't touch today because they are more state of the art. So regarding CO2 corrosion for carbon capture, for geothermal, tribocorrosion under hydrogen environments, and will be very challenging. So we are working to get invited speakers, so from different relevant topics, and we will also combine this conference with a postgraduate course that will take place at the Technical University of Vienna the day before the conference. The course will be given by Stefano Mischler, Ana Igual Muñoz, and Nuria Spallargas. So if you are joining the conference, you will have also the possibility to attend the course the day before, which will be more detailed to what I gave today, because will be at least, I think it will be at least 12 blocks of 45 minutes each. So a very detailed course where to have the chance to get more accurate and more detailed information about tribocorrosion, and then in the conference get to know all other colleagues on these novel topics of tribocorrosion dealing towards decarbonization and all these actual social relevant topics. So with this, I am at the end of my presentation. So just to wrap up, tribocorrosion is basically where degradation in a reactive environment. The consequences are difficult to predict, so you need to test them under the same conditions that you will have in the field. So never rely on separate wear and corrosion experiments. But these methods can be used for material selection, for material design. The techniques are the same. Doesn't matter if you work with biomedical implants, with offshore. You can rely on all these methodologies that I showed today for evaluating your materials and making scientific-based decisions on which materials to use. And we expect also tribocorrosion to remain crucial in the future in sustainability, decarbonization, and low carbon technologies for all the reasons that I mentioned, due to CO2 tribocorrosion, hydrogen embrittlement, and also with the onset of water-based lubricants, we will have for sure much more problems dealing with tribocorrosion when compared to nowadays, where lubricants are based on lubricants that are non-water-based. Also, if you have electric vehicles with charges, you will have many issues related to tribocorrosion for the reasons that we have discussed today. So with this, I would like to thank the Austrian Comet program for funding all this research that we have been doing and my talk. And also would like to thank all of you for your attention, for the questions, for the interest, and for the great participation on a Friday afternoon in Europe, morning in the States, and I guess it's already evening in some places in Asia. So thank you for being here, for joining. If you have some questions, I will be here for now longer time. But for those willing to get in touch with me, you are free to contact me under this email address. So thank you.
Thank you, Manel. Really outstanding. Learned a lot personally. There are a lot of questions, and I'm very happy that today I'm not dealing with those. So either of Manel need to deal with that.
Yeah. So indeed, there are quite some questions. So I'm wondering, how do we do that now? Do we just read, or do we ask people to ask the questions themselves? Yeah. Let me start. So there is a question about, I'll read it. So we observed OCP in positive potential around 40 millivolt, but when we're performing TAFL
corrosion potential,
E-core is showing around negative 200 millivolts. Why this difference? If you could explain that.
So I guess it depends probably on your polarization curves, I guess, on your which scan rate are you using. Basically, the OCP is the corrosion potential that you have in equilibrium. So you leave the sample there in the electrolyte and leave it until reaching equilibrium. In a polarization curve, if you make the scan, the position of the corrosion potential may change depending on how fast you do the scan. So that's probably the reason why if you perform a very fast scan, you may have differences between the static OCP that you observe during immersion and the one that you get from the polarization curve.
And there's a question on temperature. So does temperature affect tribocorrosion?
Sure, yeah. Yeah, I mean, tribocorrosion affects the reaction rates, and since the reaction rates are affected, then the total tribocorrosion and the wear will be affected as well, yeah.
Yeah.
This is also Arrhenius type of
yeah, for the chemical reactions for sure. The mechanical part will be maybe less affected, but since you have the combination of both of them, for many systems will be very relevant that you are under higher reactivity, for so that you will be promoting some reactions due to the higher temperature.
And there's a question on using the ball material. Is it constant for all the experiments? I think that's the question.
I think actually, yeah, but please continue.
Yeah, I think I already went through it before during the talk and now in the question. So we use aluminum oxide because it's non-reactive, because it's inert, and you avoid a galvanic coupling between the sample and the counterbody, because then the data is more difficult to interpret, because then you are not measuring the OCP of the sample, but you are measuring the galvanic potential between both of them. You can use any other ceramic. People use other ceramics, so it doesn't need to be aluminum oxide. Just need to watch out that the ceramic itself is non-degraded under this corrosive material that you will have. So the more stable the counterbody, the better, because data will be much easier to interpret.
And the next question is on magnesium alloys, and they are testing it, and there is no drop in the OCP, and OCP is raising during and after sliding. What might be the possible reason for that?
Yeah, I think we already went through this one in the previous break. So magnesium is an active metal. So when you rub through it, basically it might be that you are increasing the corrosion rate outside the wear scar, because the galvanic coupling is different. So in that case, the wear track is not anodic, it's cathodic, and the rest of the material is the anodic one. So you are triggering basically accelerated corrosion outside the wear scar. So that's the reason why probably these researchers see increase in the OCP during rubbing.
Before going to the next question, I have a question regarding the cartilage tribocorrosion. So in the I work on cartilage in the osteoarthritic patients, and we have different setups for testing the tribology of cartilage. That's like stationary contact area, migratory contact area, and things like that. So metal is a very different material in comparison to the cartilage itself, because cartilage is a biphasic material. So why is there a question regarding the using a metal as a for the semi replacement surgeries? Like why a metal rather than using a cartilage-like material like hydrogel or things like that. So,
I mean, hydrogels would be a nice replacement, and actually is a topic of high interest now, but on research. So there are no solutions yet, to my best knowledge, commercially available that rely on hydrogel. So I think that the main issue here is the mechanical properties. There are some works dealing with double network hydrogels. We are working also on that topic as well. But until now, there are no hydrogel material with sufficient mechanical performance to deal with this cartilage replacement. There are other alternatives. There are works done in Chicago by Roche Medical Center, also in Imperial by the colleagues Daniele Dini and others, where they investigated ceramics. So aluminium toughness zirconia is a very good candidate, or even PEEK. We are also working on that topic now. So polymers. These, I think, are more realistic materials than hydrogel for the short term. So hydrogel, I think, is a very good one, but maybe in the long run. So at the moment, probably those ones are going to get the cutting edge. But until now, the state-of-the-art commercially available, to my best knowledge, the only company is a Swedish one that produces this tailor-made metals for patients based on magnetic resonance of the knee. They are done of copper chromium. So
okay, yeah. So there's one follow-up question for that. I'm sorry. With respect to cartilage lubrication mechanisms, we do have different mechanisms which will work simultaneously, like boundary lubrication, hydrodynamic lubrication. So in your experiments with respect to testing, what mechanism did you even consider for the cartilage versus metal?
In our experiments, in that particular case, at the moment, we have been working with PBS. It means we have a very low viscosity, much lower than synovial fluid. And we are under boundary lubrication. We have a migrating contact area to allow the cartilage to rehydrate, and that's the reason why we have very low coefficient of friction during the experiment. But we have a simplified electrolyte or a simplified simulated body fluid in that particular case. We did some experiments having hyaluronic acid added to the PBS and BSA. But most of the work we have done has been with PBS alone because of the simplicity mostly.
Yes, perfect. Thank you. Continuing with the next question here, would a hard chromium coating be good for steel surface to avoid tribocorrosion?
A hard chromium material,
coating.
Yeah, hard chromium coating. In principle, yes. The question is that hard chromium is of high concern due to environmental reasons. So there have been a lot of research in the past 20 years to replace hard chromium in all these applications where possible, particularly in the European Union. They have done a lot of work, for example, with thermal spray coatings. Nuria Spallargas worked a lot 20 years ago on that topic. There are many publications, and probably I would say that on the long run, for environmental issues and probably some regulations that will apply in most countries, it will be interesting to find good replacements for most applications of hard chromium. So hard chromium, I think at the moment is living in some applications, I think in aeronautics and really all the critical applications where you do not have really a good replacement, but in most of them where there is a potential replacement, hard chromium is less of consideration nowadays.
Cool. Thank you. The next question is it possible to associate the electrical double layer in solution with metal corrosion in tribological experiments?
Yeah, I didn't talk about that today. So we have seen that we can do polarization curves, that we apply a potential during the experiment, that we track the OCP. One thing that you can do during the experiment as well, during rubbing, is do what it's called electrochemical impedance spectroscopy. So this basically relies on applying a small voltage amplitude, sinusoidal, signal with a small voltage amplitude, so it's non-destructive because the amplitude is going to be plus minus maybe 20 millivolts close to the OCP. And then the frequency of the signal, you can make a scan ranging from megahertz down to even millihertz. It's going to take some time, but well, hertz if you want to go a bit quicker. But basically, doing this frequency scan, you can track or trigger many phenomena that are time dependent in the electrolyte, like formation, double layer formation, and you can get information of, for example, different phenomena that take place at different time scales, like ion motion that maybe is a slow phenomena that will occur at lower frequencies. So if you want to observe all these kind of phenomena, then EIS is the proper way to go. For active metals, you can also do linear polarization resistance, because I mean, for active metals, this is basically the same, but it's just applying a constant voltage, maybe plus minus, just a ramp, plus minus 20 or 10 millivolts around the OCP. But this works mostly only for active metals. If you have passive metals, then LPR in the anodic domain will not be so accurate due to the formation of this double layer. In that case, I think IES is much better.
Yeah.
But it will be,
Perfect.
I mean, unfortunately, I skip it due to, for the sake of time. But yeah,
I think we should, yeah,
for the
perfect.
sake of time.
Thank you. Yeah, we should wrap up this because there are a few more questions here. Maybe you could reply to them later on in the chat. Yeah,
the email is there as well. So your email one, it's pretty big, so I'm sure Manel will try to answer you in due time. Also, the video, the recording will be available in TriboNet, of course, as usual. So and there's in the section of comments, many times there are some questions. We will make sure that Manel receives them. But thanks a lot, Manel. I think we are, well, you saw the reaction. We have still 42 people here after 1 hour and a half.
Very good. Thank you for being so late. I hope it was interesting, particularly for those without previous knowledge on tribocorrosion. I hope that at least they got some very fundamentals and now have some ideas on where to go, where to get further information, and can be more successful in that topic. It's very challenging, very interesting, and encourage many people to do research on this. And yeah, I will stay maybe a bit longer just to reply these questions in the chat to let them answer. And thank you again for inviting me, for having me here this afternoon. And if you have any questions, just contact me at this email address.
Thank you, Manel. You are welcome to repeat whenever you want. You know that.
Okay. Thank you very much.
Thank you very much, Manel. Yeah,
thank you so much.
So, have a good day, everyone. Thanks for being here.
Good weekend.
Bye.
Thank you.
Bye.
Bye.